So, we are going to be looking at several different ways of finding zeros. One of them being Descartes' rule of signs. Maybe you heard of that. Okay, so, no, remember we've got lots of different types of numbers, right? One of the things we're going to be looking at first is rational zero. What is a rational number? Any number that can be written as a fraction, yes. Any number that can be written as a fraction is rational. So square root of 2 is not rational. 3/5 is rational. 2/3 is rational. So one of the rules we're having is a way of finding what your rational solutions are, or what are possible rational solutions. So if I had f of x equals x to the third plus 4x squared minus 6x plus 20. So if we have something of this form, we can list all the possible solutions to this that would be rational numbers. They always come from the number that would be here and the number here. So in this case, what's the first number? 1. Okay, so 1. I'm going to put that in here just because for now. This number we're going to call Q, this number P. Does this seem familiar? Like algebra 2 something? Okay, so rational solutions remember, this is a symbol for rational, are always of form P over Q. So we're not just saying the number P, any factor of P over any factor of Q. So what are all the numbers that go into 20? Okay, so 1, 2, 4, and what are all the factors that go into 1? They have plus or minus 1. So how many possible solutions are there? Possible rational solutions, I should say. Okay, there are 12 numbers we would need to check. So in this case, those are the 12 numbers that could be solutions that are rational. These are not saying these are the solutions. If you actually check them, you have to plug each one of them in. Yeah, that's quite a few numbers to plug in. What if instead of a 1 here, what if we had say a 4? We'd have a bunch more numbers we have to plug in. Because we have to do all of these divided by 1, all of them divided by 2, all of them divided by 4. So we want to simplify things a little bit, right? Rather than not have to plug in however many numbers there are. We have to figure out a bit more focus. This is where Descartes' rule of signs comes in. Anybody heard of him? Descartes, or the rule of signs? So I'm going to do a arrangement, a helpful arrangement for this. I'm going to erase this so I can still see the function. First we want how many total complex zeros does this have?
3.
Okay? Yeah, there are 3 solutions. Where are you getting 3 from?
Degree.
Yeah. So this is the fundamental theorem of algebra: is that a degree in polynomial has in solution. So if it's a third degree polynomial, we know there must be 3 complex solutions. Now, this does not mean 3 distinct solutions. What do I mean by distinct? Different. So for example, if I did x minus 1 to the third, what's the degree of it? 3. What is the solution? 1 with the multiplicity of 3. So this would have 1 as a solution 3 times. But there are 3 solutions. It's just 1 every time. That's what when we say complex solutions. There are three complex solutions. They may or may not be the same or different, but that's what we have. Next number, we're looking at positive real.
What is that three?
Complex. So complex numbers mean either real or imaginary solution. So, to get the number of positive real solutions, we're going to be looking at the numbers here and see how many times does the sign change. So this is a positive, this is positive, just going across. Does it change to go from positive to positive? Okay, then I go positive to negative. That's one change. Negative to positive, a second change. So there are two changes. So there are two. However, we also have to do every multiple of 2 less than that. So 2 or 0. If, for example, we had 8, we'd have 8, 6, 4, 2, 0. Well, every multiple of 2 less than it. So 2 is a multiple of 2. 4 is a multiple of 2. So you do, for example, this one, 8 minus 2, 8 minus 4, 8 minus 6, 8 minus 8. So you're going to go all the way down to getting 0 or 1. Okay, again, odd number. So if we had, say, 7, okay, we would do every multiple of 2 less than that down to 1. 7, 5, 3, 1. And this is the possible number of solutions. So we know, guaranteed, there are 3 complex solutions. There could be 2 positive real or 0 positive real. That's all we're saying. There could be 2 positive real solutions or 0 positive real. Next one, the negative real. This one gets a bit more challenging. To do this one, we're going to look at a function. Any of them with an odd exponent, change the sign. So this one has odd exponent, so this was positive, we're going to make it negative. Even exponent stays the same, so we're going to keep it positive. Odd exponent, just 1, so we change it from negative to positive. Even exponent, keep it the same. Okay? So how many sign changes are there here? 1. So that guarantees we must have a negative real solution. We can't not have it.
So does that mean when you factor it, or the factors would be x plus something?
Yes. Yes.
You can explain why the negative 6x didn't change?
Okay? So it is a positive exponent, right? Or odd exponent, I mean. So we change it from negative to positive. Any of them with an odd exponent, we're going to change from negative to positive. Well, if it's positive, we would change it to negative. Like this one, we had an odd exponent. Therefore, we change it from positive to negative. So there are 2 changes. So we're not saying how many changes that we made. It's now that we've done the change, how many of these we're going to cross through the change.
Wait, what are you doing with the positive exponent?
Well, all of them are positive exponents. If you don't have positive exponent, it's not a polynomial.
No, I mean an
Odd?
exponent.
If it has an odd exponent?
No, even.
Even. If it's even exponent, you don't swap the sign. You have to swap and one swap and one change. Basically, it's like if we're plugging in negative x into our function. If we plug negative x into this, is it going to become positive or negative? It's going to go from positive to negative, right? If we plug in negative x. If we plug in negative x in here, negative x times negative x, still it's x squared, so it doesn't change. If we plug negative x in here, negative x times negative 6 is positive 6. This one, plug in negative x, nothing changes. Yeah. Well, it must have 3 solutions total. No, it cannot have 3. It must have either 2 or 0 positive real. And it must have 1 negative real. Right, hold on. Remember, these are real complex numbers. Because notice, that's the next thing I'm going to add here. is imaginary. Note, any solution that is real is not imaginary, right? So, if I had 3 complex, that's our 3 total solutions. If we have 2 positive real and 1 negative real, how many imaginary would we have? 0. How about if we had 3 complex, 0 positive, and 1 negative? Then we'd have to have 2 imaginary. So we either have 0 or 2 imaginary, and then 2 or 0 positive real, depending on which way we go. So I want to do a PowerPoint that shows this a bit better, I think. That one. Okay, so there's the solution. So if we want the number of solutions, the complex solutions, positive real, negative real, and imaginary. So first, 4 complex real, or complex solutions, not complex real. 4 complex solutions. Everybody see that? Where that came from? Okay. So now, this is a positive. This is a negative. This is positive. That's the second one. Positive, negative. So there are how many sign changes? Well, there's positive, negative 1, negative, positive 2, positive, negative. There are 3, which means there are 3 or 1 positive real solutions. We always do multiples of 2 less than. We start at whatever number we started at, and then go by 2's less than until we get down to 0 or 1. Okay. Now, this is our original function up here. If I plug in negative x into it, what does 2x to the 4th do? Same thing. It's negative 11x cubed. It becomes a positive 11x cubed. If I plug in negative x into this one, stays. Negative x cubed changes. Negative x cubed stays. Okay? Everybody see that? So now we're going to look across this. How many sign changes are across here? We have a positive, 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 negative, negative. So there's 1 change here from positive to negative. So we have 1 negative real. Everybody with me? Okay? For which one? Okay? So, this is positive because it's a positive 2, a positive 11, a positive x squared, a negative 60, negative 24. Because it went from positive to negative here. Yes. I went through and said f of negative x right here. Okay? Now we say, how many imaginary solutions? Well, you do 4 minus 3 is 1, minus 1 is 0. So it could be 0 imaginary. There you go. 4 minus 1. Minus 1. 2. So there are either 0 or 2 imaginary solutions. On the test, I usually put 1 or 2 problems that are like this, where I ask you how many complex are real, how many positive real, how many negative real, how many imaginary, all that type of thing. Now, if we want rational solutions, what is P in this case? 24. It doesn't matter whether it's positive or negative, because all of them we put plus or minus. What is Q? Okay? So you got P and Q. So here are all the factors of 24. All the factors of Q. Everybody understand where I got that right? All numbers go into 24. So now I'm going to do, so first of all, whatever P is, we can always just go with all the factors of P. Because all of them divided by 1 is just themselves. However, notice the 2 got bigger because this is going to have some fractions. So we're going to have 1 divided by 2 is 1/2. 2 divided by 2 is 1. We already have 1 in our list, so we don't have to add it again. We have 3 divided by 2. We have 4 divided by 2, which we already have on our list. 6 divided by 2, which we already have, and so on. So we actually only get 2 additional solutions that are fractions. Because if we did 24 divided by 2, we get 12. 12 divided by 2, we don't get anything other than just those two additional fractions. So how many possible solutions do we have? Three, 6, 7, 8, 9, 10. So 20 possible solutions to plug in. Now let's figure out how to actually plug in. So we're going to have to plug all these numbers in. I'm going to show you a shortcut on how to do it on your calculator. If I forget, remind me. But there's a shortcut that will save you a lot of time. Because let's go, all these are solutions to the next thing. So these are the possible things I had before. Same function. We're going to plug them all in. So if I plug in -1, I get -60. Plug in -2, I got 0, which means -2 is one of my solutions, or one of my zeros. Because our goal is which ones make equal to -2. Now, why did I stop plugging in negatives? Because we already said there was one negative real, right? On the last screen, you said there was one negative real. Once I find that one, I don't even have to look anymore at the negative number. So now, I plugged in all the rest of the positive ones all at once. As much as I want to show you on the calculator how to plug them all in at once, so you don't have to plug each one in individually. Now, how many solutions do I have in my list? 3. How many do I need? 4. Which means I still have to plug in my fractions. And note, I'm only plugging in the positive ones. Why? Because I already have my one negative solution. And so now I have my 4 solutions there. So when you're doing one of these, there's first figure out how many total solutions there are is very useful, because then you know when to stop looking. Find how many positive solutions there are, positive real. Once you have that number, we can stop looking at positive. Find the negatives. Once you have that number, we can stop looking. Imaginary solutions are generally what's left over. Do you see any patterns to the imaginary answers? Okay, we had 0 and 2. How if I did this one mistake? X to the 5th minus 4. Okay, how many complex solutions? 5. Positive real. 1. Negative real. Notice if I change the odd one, this becomes a negative. Is it still negative? No changes, so there are 0 negatives.
4.
So complex, or imaginary I should say, there are 4. Guaranteed there are 4 imaginary solutions to this problem. What do you notice about the numbers in the imaginary row? We have 0, we have 2, we have 4. There are even. Guaranteed, if you have imaginary solutions, they are even. There's an even number of them. Consider when we did the quadratic formula. We had b squared minus 4, or minus the square root of b squared minus 4ac. What comes before this? Plus or minus. So negative b. But we look at this. If we had imaginary solutions here, how many did we have? So if b squared minus 4ac is negative, how many negative solutions do I have? 2, because of the plus or minus. So imaginary solutions always come in pairs. You stuck on that idea? Okay? So the idea is, if I is a solution, then negative I is also a solution. It is actually the complex conjugate theorem, or the conjugate. So, everybody heard the term conjugate when referred to that. What does it refer to? Okay? So if you see 2 plus square root of 2, the conjugate of that would be 2 minus the square root of 2. If you had 4 minus 3i, conjugate of that? 4 plus 3i. And notice these are complex conjugates because they have complex numbers. However, the interesting thing about this is if one of these is a solution, if 4 plus the square root of 2 is a solution, then 4 minus the square root of 2 is also a solution. And it comes back to because of this plus or minus right there. If 4 minus 3i is a solution, then 4 plus 3i is also a solution. So these complex solutions and even conjugate solutions always come in pairs. Now, would this be a real number? Yes. It's a real number? Yes. Okay, so if we did, let's say, 4 minus I. If 4 minus I is a solution, what else is a solution? Okay, how about this one? 2i minus 6. No, not 2i plus 6. Negative 2i minus 6.
Oh. You just say
Here's the I part, the complex conjugate. So this comes into play sometimes when we're gonna ask is, say, give me a polynomial that has these as solutions. So x naught equals 3 and maybe 2i.
X.
So first we have
X minus 3.
x minus 3.
X minus 2i.
Yeah. So we would have to write something out like this.
Would you have to like follow that?
Yeah. What is this going to be? If you multiply these together.
X plus 4, X 5.
Or x squared plus 4. For these two. Just like if we had x minus 2 times x plus 2, what do we get? X squared minus 4. If we use imaginary numbers, it's what?
Wait, what's I squared?
What's that squared? I squared negative 1. And we can multiply those together. We get x cubed minus 3x squared plus 4x minus 12. Okay, so let's do that. Show you how to I'll plug all the numbers in quickly. So let's do a problem here. Okay, x to the 5th minus 11x to the 4th plus 49x cubed minus 147x squared plus 360x minus 432. How many complex solutions? 5. Everybody got that?
Yeah.
That's the easy one. Positive real. Let's say we have, there's 1 change, 2, 3, 4, 5. So 5, 3, 1. Okay, negative real. That becomes negative, stays negative, becomes negative, stays, becomes 0. Okay, so 0, 2, or 4. Where's 0 coming from? Yeah, 5 minus 5 would be 0. So, now, what are the possible rational solutions? Yes. So, possible rational. What number are we look at? The 432. So we have plus or minus 1, plus or minus 2, plus or minus, does 3 go into it?
Yeah.
Okay, so 3, plus or minus 4 goes into it. It's 5. 6 goes, 7, 8, 9, 10, 12, 14, 15. What's it? 16? 17? 18 does? 19, no. 20, no. 21? 24? Is 24 square root of 432? But 24 times 18. 24 times 18. Okay, so now, once you get past the square root of 432, which is somewhere between 20 and 24, it's a irrational number, we can just say 24 times 18, what's 432 divided by 16? 27. What's 432 divided by 12? 36. 432 divided by 9? 28. What? 48, okay. And 54, and 108. 44. 216, and then our last one, 432. So, if it asks you to list the possible rational solutions, then we've made a list. Then it asks you, some of them will ask you, find which one's actually our solution. How many of you want to plug all those numbers in? Okay. So we're going to do a shortcut. Using your calculator to do it. It's one of the reasons why we use graphing calculators, because plugging all those numbers in without a graphing calculator can take a really long time. So, put your equation in for y. So let's see, we had x to the 6 minus 11 x to the 4. That's right. Plus 49 x to the 3rd. Okay, so once you have it all entered in, we're going to go to table setup. So we're using our table. So table setup right there. And for your table start, put your lowest number. So what's the lowest number in this list? Negative 432. Negative 432. Now, delta table, you put the smallest increment. So if you have fractions, the fractions you put 1/2. Like 1/2 is a fraction there. If you had 1/4 in your thing, you would put 1/4. Yes. But the smallest difference. If you took the absolute value of the smallest one absolute value. So if we had fractions, you would put the smallest fraction. In this case, we have no fraction, so we're just going to put 1 in. Okay? Then you go to your table. And our goal is looking through the y1 until we get into 0. Now, since we started negative 432, it's going to be a long way to the next one. So we actually can skip it, and what's the next smallest after negative 432?
All the negative numbers.
Negative, yeah, we know the 0 negative solution, right? So we don't even have to do the negative. However, if you were still looking at the negative, you'd put the next, whatever the next smallest one is, you can look at the table and scroll through it. But since we already know there's no negative solution, because of what we did originally, we're going to skip all the way till we get to 1, our smallest positive solution. And we're looking for 0. Do you see any in the list? So 3 and 4 are both 0. Now we keep looking, is there any other ones in the list?
Do you have to look for an exact 0, or can it be like e to the 1?
You can have e negative, like e negative 5. If you see one of those, that would also work. What?
Can we just keep going until we get
Yeah. However, no. Once we get past where the answers are bunched together, so let's see, we had after about maybe 108, you might just skip directly to these other numbers. Yeah. Once we get the bigger spaces between them, because once we can get fairly quickly go to 72. Was there any of them that were e negative numbers? Well,
Why be positive?
okay, E positive, but that's a really big number, not a small number. So there's 72. It looks like it's just growing infinitely. So I would assume that those were the only two solutions. However, notice, how many positive real solutions are there? There can't be just two positive reals. However, the problem is, remember, here we were talking about rational. This does not find irrational solutions. So the question, if it asks, the question will probably ask, find rational solutions. So we might, we know there's another rational solution, at least one more, or one more real solution, I should say. It's not necessarily rational though. Yeah. Yeah. I usually look at the graph and do that, but this is oftentimes faster because usually you don't have all the way to 4 to use that small number. And this will find all of them all at once instead of having to do a search for each one individually. Okay? So, let's see, what else do we need on this? I think a good start for it. So,